Hello everyone, I am Abhishek Datta and you all are watching my YouTube channel Mathematics Made Easy. Today in this video I am going to discuss about a very vital concept of modern mathematics known as the derivative of a function. So derivative has its wide application in various branches of mathematics, and without the concept of derivatives it is not possible to study advanced maths. In the field of engineering, in dynamics, in statics, and also in various other sciences, derivative has its core applications. So let us today try to understand what we mean by derivative. It is a very important mathematical tool used in calculus. So basically derivative means the rate of change between two variables, among which one is a dependent variable, the other one is an independent variable. That is, if we have a relation established among two variables, say x and y, among which one is treated as the independent one, the other one as the dependent one, then derivative gives us the rate of change of the dependent variable with respect to the independent variable. So let me elaborate the concept in details. For example, let us consider y as the dependent variable and x as the independent variable in our discussion. So we have a function y equal to fx. So here we consider a function y is equal to fx, where x acts as the independent variable and y acts as the dependent variable. So by derivative we mean the rate of change of y with respect to x, that is the rate of change of the dependent variable with respect to the independent variable. So basically derivative measures the rate of change between the two variables. Now what we mean by such an expression, rate of change? So to elaborate the concept, let us consider y as x cube minus 3x plus 2. So y is expressed explicitly in terms of the variable x. So as we observe here that x acts as the independent variable, because first we have to input the value of x to obtain the value of y. So the value of y depends on the value of x. So x is free to take any value. The value of y depends upon the input of x. So here x acts as the independent variable and y acts as the dependent variable. Now if the independent variable x undergoes any change, say the independent variable x undergoes a change of amount delta x, this is the change which the independent variable suffers, a change of amount delta x. So as a result, as a consequence, the dependent variable y should also undergo a change because y is linked to x. So if x suffers any change, as a result y will also suffer a corresponding change. Say the corresponding change in the dependent variable y is denoted by del y. So delta y represents the change of y corresponding to a change delta x in the independent variable x. So if now we consider the ratio of these two changes, that is ratio of the change of the dependent variable y to the ratio of the change of the independent variable x, this ratio del y by del x is known as the relative change of y with respect to x. This is the relative change of the dependent variable with respect to the independent variable. Now if this relative change be subject to a limiting condition, when the change of independent variable becomes infinitesimally small, that means the measure of this ratio when the change of the independent variable delta x becomes infinitesimally small, which means if we take limit over this ratio when delta x tends to 0, that is the independent variable x undergoes an infinitesimally small change, then this limiting value is known as the derivative of y with respect to x, and we denote this by the symbol dy dx. This is the symbol, where ddx is the differential operator. This is known as the differential operator ddx applied over the variable y. Mind that this is not dy divided by dx. We are not dividing dy by dx. This is ddx over y, where ddx is the differential operator which is applied over y. So basically, by derivative of a variable y with respect to a variable x, we mean the limiting value of the relative ratio, that is del y by del x, when del x tends to 0. That is when the change of the independent variable is infinitesimally small. Then the value of this limiting ratio is said to be the derivative of y with respect to x, or the rate of change of y with respect to x. So this is the basic concept or the analytical definition of derivative of a function y with respect to a function x. So as we consider here y to be a function of x, so as we discussed that initially, say these are the values of x and y. So initially x suffers a change of amount delta x. So the final value of x is given by x plus delta x, and as a result the dependent variable y undergoes a change of delta y. So the final value of y is given by y plus delta y. So these are the initial values of x and y, and here we have the final values of the independent variable as well as the dependent variable. So in this function, if I now replace x by its final value x plus delta x, then at the same time we also have to replace y by its final value, that is y plus delta y, because when x suffers the change, y also suffers the change simultaneously. Delta x and delta y are simultaneous changes over x and y. So when the variable x changes to x plus delta x, at the same time y also changes to y plus delta y. So if we apply these transformations in this function y equal to fx, that is, if I replace the independent variable by its final value, that is x plus delta x, at the same time we have to replace the dependent variable also by its corresponding final value, which is y plus delta y. So from here we can express delta y as f of x plus delta x minus y. We simply shift y that way. So we have delta y is f of x plus delta x minus y, or we can write delta y as f of x plus delta x minus fx. Y is given by fx, that is the value of y. This is the expression for delta y. If we now divide both sides by delta x, dividing both sides by delta x, we have this result. Delta y by delta x is given by f of x plus delta x minus fx whole divided by delta x. And finally, taking limits on both sides as delta x tends to 0, applying limit on both sides when delta x tending to 0, the left hand side becomes the derivative of y with respect to x. This is the definition of dy dx as we discussed earlier. So here we have dy dx, the left hand side becomes the derivative of y with respect to x, dy dx. So which is thus given by limit of delta x tending to 0, f of x plus delta x minus fx divided by delta x. So this is an alternating limiting definition. This is an alternating limit definition for derivative of y with respect to x, which is given by limit x tends to 0, function of x plus delta x minus fx divided by delta x. So this limiting definition is known as the first principle of derivative. So here what we have finally, that if we have a function y is equal to fx, then the derivative of y with respect to x dy dx is given by limit of delta y divided by delta x when delta x tends to 0, which is also given by, this limit is also given by limit delta x tends to 0, function of x plus delta x minus fx divided by delta x. So this second form of limit, this second form of limiting definition is known as the first principle of derivative. We call it the first principle or the limiting definition of derivative. So this is known as the first principle of derivative. So basically derivative of a function is nothing but to evaluate a limit itself. So we can express derivative in terms of a limit. This is the first principle of derivative. And many authors consider del x to be h. In many Indian books especially you will find that they represent the increment or the change of the independent variable by the symbol h. So therefore the derivative definition becomes dy dx is given by limit h tending to 0 f of x plus h minus fx upon h, which is known as the first principle of derivative. Now let us try to find the derivative of some functions applying this first principle. For example, let us consider fx to be sin x. Say we have a function fx is equal to sin x. So here y is equal to fx, which is given as a sine function, sin x, and we have to find the derivative of y with respect to x using the first principle of derivative, that is using the limiting definition. So how to do so? So as we know that dy dx is given by limit h tends to 0. Here h means delta x, that is the increment of the independent variable, f of x plus h minus fx divided by h. So here fx is given by sin x, and hence f of x plus h is given by sin of x plus h. This is the functional property. Fx is sin x. To get f of x plus h, we replace x by x plus h here. So fx plus h is given by sin of x plus h. So upon substituting these values in the limiting definition here, we thus have dy dx is equal to limit h tending to 0, fx plus h is given by sin x plus h minus fx is given by sin x upon h. Now here the numerator, as you see, is of the form sin c minus sin d, that is the trigonometric form of transformation of sums and products. We have this particular form in the trigonometric chapter known as the transformations of sums and products. So we apply that formula now. So this is equal to limit h tends to 0 sin c minus sin d. This is given by 2 cos of c plus d by 2. That is the formula for sin c minus sin d. That is 2 cos of c plus d by 2, sum of these angles. So 2x plus h by 2 into sine of c minus d by 2. So c minus d, x will get cancelled. So we have h upon 2 and whole divided by h. So here we apply the formula sine of c minus sine of d given by 2 cos sum of these two angles c plus d by 2 into sine of difference of the two angles c minus d by 2. You will find this formula in the trigonometry lessons in the chapter known as the transformations of sums and products. So now we consider this limit as limit h tending to 0. If I consider sine h by 2 divided by h as a single function, and we also divide the numerator and denominator by 2. So here we have h upon 2 and these two get cancelled from the numerator. We are dividing both the numerator and denominator by 2. So these two getting cancelled, and here we have h by 2 into limit of cos of 2x plus h upon 2 when h tends to 0. So we are splitting these limits into two parts, into two halves. One half is sine h by 2 by h, and we are dividing the numerator and denominator by 2. So this portion multiplied by limiting value over this cosine function, limit of cos 2x plus h whole by 2, h tends to 0. So as we know that this limit is 1, we can also write h by 2 tends to 0 instead. So this is the standard form of trigonometric limits. Limit of sin x by x, x tends to 0 equal to 1. I hope that the students have the basic knowledge of limits here. So this is the standard form of trigonometric limit. This is 1. So we are left out with limit of h tending to 0, the second limit, that is cos of 2x plus h divided by 2, because the first limit is 1. That is the standard form of limit. Limit of sin x upon x, x tending to 0 is equal to 1. So the first limit is in this module, limit of sin x upon x, x tends to 0, this becomes 1. Now here in this limit, if we again replace h by 0, so basically we have cos of 2x by 2, which is given by cos x. Mind that in this limit, x is treated as a constant. Here h is the only variable because the limit is over the variable h. So here x is treated as a constant while evaluating the limits. So thus finally we have dy dx is given by cos x. So this is the first standard form, or the first standard formula also you can say, of derivative, that d dx of sin x, we here obtain dy dx is cos x. So what is y? Y is taken to be sin x. So thus we finally have d dx of sin x is given by the function cos x. This is the first standard form of derivative. We consider this to be one of the standard formulas of derivative. D dx of sin x is equal to cos x. Similarly, we can also obtain derivative of the cosine function. Let us now try to obtain the derivative of the cosine function, d dx of cos x. So the procedure is almost similar. Now we consider y to be the cosine function, the standard cosine function of x, that is cos x. So we have y is equal to fx is equal to cosx. So recalling the definition of derivative, we have dy dx is given by limit h tending to 0 f of x plus h minus fx upon h. So here fx is given by cos x, hence f of x plus h, we simply replace x by x plus h here. So f x plus h is given by cos x plus h, and substituting these values in the limiting definition, we thus have dy dx is equal to limit h tending to 0 cos x plus h, that is fx plus h, minus fx, which is cos x, divided by h. And again the numerator is of the form cos of c minus cos of d. That is also a particular form of the transformations of sums and products in trigonometry lessons. So we apply the formula here. So this is given by limit h tending to 0 cos c minus cos d. This is given by twice sine of c plus d by 2. So sum of these two angles by 2, which gives us 2x plus h by 2. So this is 2 sine of c plus d by 2 multiplied by sine d minus c by 2. Mind that here the formula is 2 sine first plus second by 2, then multiplied by sine of second angle minus first angle by 2, sine of d minus c by 2. So this will give us sine of minus h upon 2. If we apply second minus first, so x minus the entire x plus h, which is minus h upon 2, whole divided by h. So this minus sign now comes out of the sign ratio. So we can take the minus sign outside the limit. So this becomes minus of limit h tends to 0. We can group sine h by 2 by h in one bracket, and also we divide the numerator and denominator by 2. So as a result, these two get cancelled. If I divide here both numerator and denominator by 2, these two get cancelled and we have by 2 here. So we consider these two together, sine h by 2 upon h by 2, because this is the standard form of limits, and multiplied by limit over this sine function, that is limit h tends to 0 sine of 2x plus h upon 2. So again, this is the standard form of limit, that limit of sin x upon x when x tends to 0. We can also write h by 2 tends to 0. If we divide both sides by 0, 0 by 2 remains 0. So this is the standard form of limit, trigonometric limit. This becomes 1. So basically we are left out with minus of the second limit, the first limit being 1. So limit h tends to 0 sine of 2x plus h upon 2. Upon substituting h equal to 0, finally we get the answer to be minus of sin x. So here dy dx is given by minus of sin x. So thus finally we have d dx of y. Here y is cos x. If I substitute the value of y here, y is given by cos x. So we finally have d dx of cos x is given by minus of sin x. So d dx of cos x is given by minus of sine function of x. This is the second standard form of derivative. So here we derived the two important standard forms. One is d dx of sin x is given by cos x, and the second form is d dx of cos x is given by minus of sin x. Similarly, we can evaluate the derivative of any function, the other trigonometric ratios, as well as polynomial function, as well as exponential function, logarithmic function, any function. We can obtain the derivative by this procedure. That is the first principle of derivative. So in our upcoming videos, I shall be discussing the procedure to evaluate the derivative of other trigonometric ratios, that is to find the derivative of tan x, cot x, sec x, cosec x, and also to find the derivative of exponential functions, logarithmic functions, to find the derivative of constant functions, and the chain rule of derivative. That is another important application of derivative, that is known as the chain rule of derivative. So those we shall be discussing in our next videos. Please do ask if you have any doubts. You can ask me in the comment section. I hope the basic concept of derivative, the basic limiting definition, the first principle of derivative, and how to apply the first principle to find the derivative of a function. We have illustrated two examples here in terms of ddx of sin x and cos x. I hope the basic procedure is clear to you all, and we shall be continuing this discussion further in my next video. Thank you all. Have a nice day.